Hey folks, before we get into today's podcast, I wanted to let you know about our upcoming QCon software development conferences. We will be back in person with QCon London this April the 4th to the 6th and online with QCon Plus May the 10th to the 20th. Join the world's most innovative senior software engineers across multiple domains in person and online as they share their real-world implementation of emerging trends and practices. You can learn more about the events at qconferences.com, and we hope to see you there. Welcome to the InfoQ podcast. I'm Charles Humble, one of the co-hosts of the show and managing editor at cloud-native consultancy firm Container Solutions. Today I'm speaking to Matthew Clark. Matthew is Head of Architecture for the BBC's digital products, a role that covers the websites and apps for BBC's news, sport, weather, children's, education and content discovery services. Over the past few years, he and the BBC's design and engineering teams have completely rebuilt the BBC's website using modern approaches and technologies such as React and serverless. And it's that migration that we'll be talking about on the podcast today. Matthew, welcome to the InfoQ podcast.
Thank you. Thanks for having me.
Before we get into the sort of architectural details, can you give us a little bit of context? How big is the BBC in terms of traffic and page types and so on?
Cool, it's pretty big. Yeah, page types certainly have more than 200 last time I counted. There's a real broad set of products, as we call it, on the site. Being public service, the BBC does a lot of things trying to find something for all audiences. So there's the really big global news. For example, probably the largest news website in the world. We've got things more for the UK-only audience like iPlayer, the VOD platform that gets millions of plays a day. And then there's all kinds of specialist stuff. Children's things, educational things, food recipes, all kinds of stuff. So it's broad, but also the traffic, the number of users we have is super high as well. Tens of millions will use the services every week, often more than that. For the US election, for example, last November, we got 165 million unique users come to our coverage, either video, audio, or text online. So pretty huge numbers. And as the technologist, that's kind of part of the fun, right? How do you build something that scales and works well and gives everyone an interactive and personalized experience as appropriate at those moments? You can't just rely on CDNs or caching. There's a real fun challenge there about offering such a great service to that many people at those big moments.
Can you give me an idea of the number of developers at the BBC as well?
Maybe in the order of about 1,000, a bit more depending on what you call developer. It's not a small team. But compared to kind of some of the big competitors that we find in the US giants and so on, it's not a big one either. So we do have a key goal to be as efficient as we can. You know, we're a public service, so we do our best to make the most of those development team. We've got as I say, big service, works with a lot of people. We need to be as reliable as we can in those really big moments because people depend on us. So we make sure that those developers are working as efficiently as they can on building great products for us all.
And broadly speaking, does the same architectures support all the different platforms and services that you're responsible for? So the various news and sports apps, internet-enabled TV, the website, BBC Sounds, and so on. Is that all sort of one fundamental architecture?
Broadly, yeah. As a lot of places do, you have different teams working on different things, so there's natural variation, but fundamentally, yes. They're all kind of working the same way. They've got the data sources from which you can then build websites and apps. And as you say, connected TV is another big one. You obviously have to work different ways for different platforms, but fundamentally, yes, it's the same thing.
And staying at a kind of high level for the time being, it's my understanding that you've been on a very sort of familiar cloud migration. So you've been moving to a public cloud, AWS in the case of the BBC, and also adopting more continuous delivery and DevOps. Is that basically correct?
Yeah, that's right. We started our cloud journey fairly early for a large org, about 2012, 2013. We started doing it. We moved some things quite early on, such as our video transcoding capabilities, and it all went rather well. So we made the call 2 or 3 years into that, I guess a few years ago now, we should move all of our online services to the cloud, the websites, the apps, and all the APIs that power it. Move that fully into the cloud. We gave ourselves a deadline of 2020 to do that. That was a good moment to switch off our data centers and move across. And that's what we've just completed.
And what was the main driver for that migration?
There's several reasons, really. I mean, fundamentally, you want to be in the business that you're in. You don't want to be doing more things than you have to, right? So looking after data centers, procuring servers ahead of time, If you can get away without doing that, you want to do it, right? But as you go on, you realize that the cloud is more than replacing your data center, right? It just does so much more. The ability to have unlimited compute effectively at a moment's notice, and the same with storage and machine learning capabilities and everything else, is just extraordinary. It opens so many doors. And so I don't think we perhaps realised that so much when we started the journey 7-8 years ago. But now it's not a fair comparison, is it, running your own data centre versus the cloud? They're just completely different ways of working. And the amount of stuff that we've done since moving to the cloud that we couldn't have done before is huge. It's now such a no-brainer, I think, for anyone doing this stuff. You've got to take advantage of that capability.
So can you give us an idea of what your architecture looked like before you started to migrate? So I think your code was mainly written in PHP. I think you were hosted in a couple of data centers in London in the UK. But can you kind of describe what that architecture looked like pre the migration?
Yeah, you've got the basics. I guess fundamentally it was like a classic LAMP stack, which was the thing you did 10 years ago. A bunch of Linux servers running Apache, running PHP, and then various data sources underneath with all your content, things like MySQL or other databases we had. Maybe a bit more than that because it's a large site. We had a set of Varnish servers doing caching, for example. We had a separate Java API layer to separate the presentation from your logic. So there was a bit more maybe than LAMP. But yeah, fundamentally, it was that running on 2 data centers, hot on both, so that you were resilient to one failing. But it was a very sensible architecture for when we kind of made that back in roughly 2010. It obviously seems old-fashioned now as technology moves on.
Right, yes, the constant sort of march of technology, I suppose. And I think you also had an interim step. I found a fantastic talk, actually, you gave at reInvent in 2017, where you were talking about nanoservices. And I think of a nanoservice as being smaller than a microservice, but perhaps bigger than a function. So I'm assuming you moved to nanoservices first and then moved to functions, though it's probably not quite as clean as that. But is that roughly right in terms of the journey?
Yeah, that is roughly right. When we started building things in the cloud, of course, yeah, as you say, we moved to DevOps model where you build it, you own it, you maintain it. And that is great from a continuous delivery point of view, right? Teams can be fully empowered to build it as they want and release it as they want. And that's great. But it does come with quite a lot of expense. All of a sudden, teams that weren't doing it before now suddenly need to think about networking, right? How their VPCs are set up, or best practice for patching OSs, or scaling, or monitoring, all these things that on the data center, we had separate operations teams looking after. And that's totally possible, of course. The kind of full stack engineer is capable of doing all those things, but it's quite a lot of work. And a team that specialized in, building great websites and good at HTML accessibility, it's quite a lot for them to learn to be good at all those things. So we looked at how this could happen. And this was, the days before serverless really was a thing, before Amazon had launched Lambda, all those kind of things. And we thought, well, we kind of wanted something similar back then. We said, we want the way in which teams can write the code they want to write and have the full power of the cloud, the ability to release when they want and so on, but not have to worry about the practicalities of operating it. And we built a platform, which is effectively like kind of cloud functions are today, where teams could upload their code, not worry about the servers they're running on and how they access it. It kind of gave you the golden path for the 80%. If you're building an API or building a web page, here's a standard way of doing it. But you've still got the whole cloud if you wanted to do something more tailored or sophisticated. And it worked well. And one of the things we found was when we gave people this service, the unit of change they wanted to make was smaller than what they've been doing before. They would change just one page or even one part of the page, or they'd change just one API endpoint rather than a set of API endpoints you might have in a microservice. And so, we dubbed this term nanoservice to this idea of this unit of change you're making was smaller than you classically would do if you were running your own virtual server or container. They're roughly the same size, I think, as a cloud function is today. And I didn't like using the word function because we already had that, of course, in programming.
Right, yes, of course.
Of course, a cloud function is a lot bigger than a programming function. So that's why we picked this term nanoservice. And I don't think it'll take off now because cloud functions are so unique, so common as a term, aren't they? But that idea of these smaller units of change, I think we are seeing in the serverless world that your designs are less about servers or microservice-sized things and more about these little tiny components that you then hook together in a chain.
So why did you move from that to Lambda when Lambda became available?
So when Lambda first became available, it was quite basic. We looked at it and we looked at what the other cloud providers were doing when they were kind of coming along as well. And it was early days for that technology. And certainly for request-driven things, building kind of websites and APIs, the performance just wasn't there. Especially the cold start time. Sometimes you would request something that could take several seconds to respond, which just isn't where you want to be, of course, when building web things. So we actually stuck with our solution for a few years. And then we got to about, maybe 2018. And serverless technology was just coming on nicely with all the cloud providers. And we realized, right, now is the point we need to let go of what we've built. This platform we built, doing these kind of nanoservices, is kind of our own kind of cloud function approach. has worked well, but as the bar raises with the cloud providers doing more and more for you, you've kind of got to follow that. You've got to stop building your own things in-house and move to what can be provided as a commodity off-the-shelf way. And that we reached that moment, we realized, serverless functions are good enough. We should be using them rather than building our own.
Were there specific reasons why you went to Lambda as opposed to, I don't know, using VMs on EC2 or something like that?
It boils down to this idea that why do something that someone else can do for you? I mean, it's obviously more nuanced than that, but you want your teams to be focusing on what's really important to the organization. You don't want to run servers, but be them physical ones in a data center or virtual ones in the cloud, right? The cost of keeping them secure and appropriately scaled, or even getting the auto-scaling right and patched, there's significant overhead to that. With serverless, you get to kind of a place you really want to get to as an organization. I've got my business logic, I've got what I want to happen. I just need it to run at the right moment in the right place. And serverless just takes away all those problems so that you focus on what really matters.
I presume it would be similar for something like, say, a Kubernetes cluster or Fargate or something like that.
Yeah, serverless in some ways kind of abstracts even more, doesn't it? Because you don't have to worry about even less concern with things like the scaling and the underlying infrastructure and how much capacity you've got. But yes, you could have also done this. We've not taken the container route just because of the path we've taken. It's a perfectly great route, of course. But because we started the cloud journey early, before kind of Kubernetes was a thing, we got really good at building VM images. And so from that, the natural step was to jump to serverless to free us up even more from the underlying hosting.
Are there specific advantages that Lambda has for your particular workloads?
As well as that kind of general less to worry about, the fact that it can scale so quickly is very useful to us because our traffic can vary so much. We can go from thousands to tens of thousands of requests per second in not that long a time, and multiple cloud providers can now provide that as a service. But the fact you can do that and you don't have to worry about auto-scaling taking a minute or two, as sometimes it can, or maybe you've not quite got every metric for when you need to scale. Is it compute? Is it memory? Is it network? And so on. You can rely quite on the fact that you have effectively unlimited compute. Each one's going to have a guaranteed set of access to CPU and memory, more or less. And that does kind of provide you with a wonderfully consistent experience for everyone. There's all kinds of other advantages too. We've found, like testing is another great one. You can create a test environment, a pre-production environment that behaves exactly the same as your production one, scale it up for maybe a load test for a few minutes, pay just whatever the few dollars charges for that. And the moment you finish your load test, it goes back to being nothing again. It's super useful for our engineering teams and making sure that our large services will behave the same as they evolve it.
I find that really interesting because a common complaint about Lambda is that it can be quite difficult to debug. Is that something that you've found? And how do you get observability into your production systems?
Not being able to kind of SSH onto the box and do some digging around is definitely a limitation. And when you get to the really gnarly things around some low-level library or network packets or something, you do miss that moment. It's not really a hit as this one because as you build your cloud functions, they're naturally simpler and smaller than perhaps what you would have built as something running on the server, right? They're typically not that concurrent, don't handle parallel requests, not very long running, short-lived. They don't have a lot of state normally. And so actually there's less to go wrong. They don't find themselves with memory leaks or getting themselves in a bad state. And when they do, you can recreate it fairly easy in your local environment. So we've not had too much of an issue. The heart of it, of course, is because you're now more distributed. You have more separate systems. So how do you understand where in the chain the problem is? We've gone big on tracing. We give request IDs from kind of the first moment they hit our system and pass that all the way through the stack. That is super useful. And of course, you make sure you get the logging right and the metrics and the alarms right as well, so you can spot when one part of your system is not behaving as it should.
So we should probably step up a level. Can you give us a kind of an overview of what the new architecture looks like in terms of sort of traffic management and how the rendering layer works and so on?
A high-level overview. When a request comes in for a web page, the first couple of layers are traffic management layers. Because we have so much traffic, reliability is super important to us. That's a really key layer for us. Handling any kind of mischievous requests coming in, making sure people are signed in if necessary, caching where appropriate to handle the load, handling any errors and so on. So that traffic management is super key. And that runs on VMs. We haven't made that serverless, just because it doesn't make sense, right? That kind of proxying responsibility where you're handling large amounts of concurrent requests and generally waiting, lots of dwell time, waiting for the underlying systems to respond, that's not a good fit for serverless today. It'll be interesting to see if cloud functions evolve to make that a more reasonable thing, but today that's an example where you wouldn't put it.
So is that sort of Nginx then, the traffic management there?
Yeah, exactly. A lot of it's based on Nginx and what you can kind of build off that. Beyond that, then you hit cloud functions. The HTML rendering part, like everyone else nowadays, we use React and Node.js and the wonderful isomorphic where the same JavaScript runs on the server and then a dynamic client update. So that gets rendered as a function. That works very well that way. And we separate that kind of presentation logic from the underlying kind of data logic of where do you fetch the data and how do you understand it and give the right thing to the right people. So that's a separate kind of effectively an API, a business layer we call it. Again, it's just more functions. So it's functions calling functions. You have a chain of functions at this point. You have to be a little bit careful how far that goes. And of course, those functions are then able to call whatever underlying data store it is to actually fetch the content to build the page. It's not a million miles off kind of the standard, back to the LAMP stack we were talking about earlier, right? Request comes in, you do it in return. You're just using functions to do kind of the grunt work, the CPU intense work, because it scales so well and there's less to look after.
So one of the things you talked about in a blog post, which was actually one of the things that kicked this whole podcast off, and I'll be sure to link to that in the show notes. But one of the things you mentioned in that blog post is the fact that your web core is a mono repo rather than, say, using web components or something like that. Can you talk a little bit more about that particular choice?
When you build a site, we found we have lots of teams working together on building the site, right? And different teams will own different pages and sometimes different components within pages. And so there's an interesting question of how do you get them, how do you allow the kind of DevOps continuous delivery thing where they can all work on their own and do their own thing and release at their own cadence, but somehow it come together to make a really great website. And we'd looked at some of the kind of web component standards out there that allow you to kind of stitch things together. And we've done other clever things in the past around kind of your edge, your traffic management, stitching together things. The problem with that approach is you end up with different teams doing different things at different rates, and it doesn't create the best web page. If you want kind of consistency in your design and using the same JavaScript libraries, like for example, we've had pages in the past, we've had multiple versions of React on them just because different parts of the page were upgrading at different time, and it doesn't lead to a fast site. Performance is super important to us. We've seen over the years done a lot of measurement on this, and if your page slows down by a couple of seconds, you will lose a quarter, if not more, of your audience. So performance is super important. Accessibility is another important thing for us. We wanted to make screen readers and so on to really understand it. So we realized we had to do this well. We needed to have one way of building a website, certainly for the common stuff, and decided to go down that mono repo approach. So we have multiple teams owning their own part of that mono repo, and we use the GitHub code owners file to help understand who owns what and who needs to review what. But then it all comes together to make one, and ultimately one deployment as a function that can render all those different pages.
Okay, and then if I'm understanding you, all of that rendering is then happening in AWS Lambda, right?
That's right, yeah. It's all happening in Lambda. It's effectively one large Lambda. We might choose to split that up in the future. But as always, you've got different projects at different stages, so not quite everything happens that way. But for our new stuff, you have that one Lambda that is able to do multiple different pages from that mono repo and multiple teams effectively contributing into that one Lambda.
Another thing that I found interesting about your architecture was that you don't have an API gateway between your traffic management layer and the Lambda functions, which is typically how it's done, and so was a bit unexpected. Can you talk about that?
We obviously looked at it because that's the standard way in which you call these functions, but we realized we didn't need it in our case because we had our own proprietary kind of traffic management layer in front of it. It was able to call the Lambda API directly. And so we didn't need to put API gateway in it. That saves a bunch of money. It also, of course, is one fewer step, a bit quicker, a bit simpler process as well.
So it's a little hard to do this without the aid of a whiteboard, but can you give me a rough sort of breakdown of what each function would be doing? So if I look at the BBC News homepage this morning, then there's a red box with navigation, you've got various headlines, you've got some sort of RSS style abstracts, you've got sections for must see, most watched, and so on. And that, we said, is all built with functions. So how does that map? Is that like one function per kind of box, or how does the mapping kind of work?
In the past, we've tried to separate those different parts of the page. Now, as we were saying before, we have that kind of mono repo for all the presentation bit. So from a HTML rendering kind of React point of view, there's one function doing that with different teams building the different components that come into that. But underneath that, at the kind of API level where the data comes from, yes, they're separate. So there's different parts of the page, the navigation and the main content and the most read, and for example, all those bits you say, that they will be separate functions, each responsible for their own whatever unique data type it is to power that page.
And you mentioned earlier that you do chain functions, but that does have cost implications, right? So I'm presuming you have some way of kind of managing that and not having overly long chains.
The fact that you're paying for CPU, whether you use it or not, means that if you've got a function waiting on another function, you're effectively paying for that dwell time, which isn't great, and that can add up. So yeah, we try and limit the depth of those function chains to no more than about 3, just so you're not kind of going that too far. It's a balance, of course, because you do want the isolation between them. it's nice to have the separation of concerns between them. So there's an internal debate always happening. How do you get that balance right? You want to optimize for cost, but you also want to optimize for performance and reliability and understanding of what's happening.
Another thing that can be a bit challenging with Lambda is setting the right memory profile. Was that something you struggled with?
There is a trial and error aspect to that. And it would be something that would be great if there could be things to help you with that more. Because you have that balance where it's a fixed ratio between CPU and memory. We had to go to a gig of memory, even though we don't actually use anywhere near that, just because that we work just on balance. That works out to be the best value overall. The fact that you would respond quicker makes it cheaper than one of the cheaper ones overall. So there is a bit of kind of trial and error on that. But we did the trial and error, we found the right answer, and we just leave it alone now and we'll review it periodically.
Cold startup times is another area where Lambda can sometimes be somewhat challenging. Is that something that you found to be tricky?
It is. It seems to have got a lot better, but it still is a problem sometimes. It can be several seconds. I mean, over half of our Lambdas will return in under 50 milliseconds. We've really optimized that, and that's great, but you do get some that can take several seconds. In the worst case, that isn't great. As a website, you really don't want that to happen. So we watch it carefully. It's fortunately a small percentage, but it is definitely one of the disadvantages of the kind of cloud function model.
And another potential disadvantage of the cloud function model is the financial cost. When your blog post was first published, there was a lot of discussion in the community, some of it honestly fairly wild speculation, around the cost, with the underlying assumption that Lambda compute cost is higher. And I think that underlying assumption is fair. So have you been able to offset that?
It is a totally valid argument because if you do the kind of raw calculation, how much does it cost to have access to a CPU and memory for a period of time, it's apples and pears, right? They're different. You can't really compare. But if you compare kind of the virtual machine versus the function cost, it's between 2 and 5 times as much to use the function. So significant. It's not orders of magnitude, but it's significant. So it was a concern I had from the start was, is this going to be a financially not great choice? I always like the idea that if you design for serverless in the kind of stateless, simple way, then moving that onto a VM or a container later is an achievable thing. So that we always had that fallback plan. It turns out we didn't need it. I mean, there is, of course, the TCO argument, the total cost of ownership argument, right? You have to do less. And I think that's a totally valid one, but we didn't need that one either because when it came to it, it didn't cost us any more to use serverless, maybe even slightly less. Just because you're not paying for compute for them any more than you have to, right? The millisecond you stop using it, it goes, and that makes a big difference. When we run APIs and websites as servers, you typically run with your CPU usage at 10 to 20%, right? That's best practice. That's healthy. You don't want to be contended on CPU or memory or networking or anything else to run a healthy server, otherwise you will not stay fast and reliable. So if you think about it, say you're at 20% CPU utilization, you're effectively paying for 5 times as much compute as you actually need. And so all of a sudden, by comparison, your serverless costs turn out to be pretty similar. It's not quite that simple, of course, because you're also not necessarily using all of your CPU in your Lambda. But if you get that right and you've got nice fast response times and lots of caching in place to make sure that your functions return quickly, what we found was it wasn't any more expensive, as I say, maybe even slightly cheaper.
That's really interesting. Thank you. How do you handle caching? I think you were using Amazon Elasticache, which is basically AWS's hosted service for Redis. Is that still the case?
Yeah, we use Redis in numerous places. It's fantastic. It's such a versatile service.
So how does Redis work for, say, caching content?
That use case is really simple. Redis at its heart is a key value store. So when we have it at multiple layers and whenever content is rendered, be it the HTML or underlying the data in the API, we simply put it in as a key in Redis with an expiry time, and subsequent requests can just pull it from there rather than re-render it again.
And presumably because Redis is storing everything in memory, that means that everything is ephemeral.
That's right. I think you can configure it to be more durable than that. But yes, the use case we have, you store it in memory. If you lose one of the servers, you will lose the data within it.
How do you cache bust if you want to force an update?
Because it's a key value that your code is writing to, you're fully in control of that. So when we do get an event in saying something has changed for whatever reason, we can update the document within it or simply mark it as stale so that next time round we can re-request the data from the underlying data source.
And do you have problems with sort of cross-region calls? I'm guessing you might take a performance hit there.
Yeah, we don't do a lot of cross-region stuff, so it's not caused too much of a problem. We notice that across the availability zones, it can certainly add up. But Redis is so fast anyway, sub-millisecond within an AZ, and not that many milliseconds across AZ. The performance has always been phenomenal anyway. We haven't done much cross-region stuff, but I suspect it's not bad anyway. And you can do master-slave, of course, as well, so you could have local replicas of your caching if you needed to.
Ah, yeah, of course you could. Yeah, that would totally solve the problem, actually, if you were to ever hit it, wouldn't it? And you said already that you're big fans of Redis and you use it quite extensively. And I know that you were using it, at least, as a queuing system, which I was intrigued by. Back in the sort of late 90s and early 2000s, I did a lot of work in both retail and investment banking, particularly around sort of early internet banking. And a lot of that was built on top of what was then called IBM's MQ series, which was their early queuing software. And it was actually a really brilliant piece of software, very solid, very reliable. The idea of using Redis for queuing therefore kind of intrigued me. Do you still do that? And if you do it, why?
Not in our latest stuff, but we do still have that operational for some of the things we've made before. I mean, it's an example of where Redis is so flexible. It is a key value store, but your values can be a range of different types, including lists and even streams in the latest version. So creating something like a queue in Redis is actually not that hard. You can push and pop things off that list effectively to be a queue. You can write Lua, which runs on the box, to do some cleverer stuff like having a dead letter queue, or even some more sophisticated things like spotting duplication in queues or having kind of prioritization, for example. Why did we pick Redis? Just because it's so unbelievably fast that you can communicate between things in a millisecond or sometimes less. It's phenomenal, whereas most of the queues are tens or hundreds of milliseconds, depending on what they are. It's an unusual choice, right? And 9 times out of 10, if you want a queue, use a queue, right? Use the right tool for the job. I wouldn't recommend it most of the time, but if you did need something incredibly fast, you were willing to accept data loss, because as you were saying before, these boxes can fail and you lose what's in memory. In a world where you're maybe tolerant of that and speed is your number one thing, it is an interesting choice.
Yeah, it really is. I'm impressed that you've been able to do things like prioritization and dead letter queues and even like handle duplication. That's more than I would have expected. It's really interesting. We're coming towards the end of our time, and I'd like to touch a little bit on some of the DevOps and more cultural aspects. Can you give us an idea of how many releases a day you're doing now via your CI/CD pipeline?
Yeah, it's a good question. Across all of, because there's an awful lot of internal tools as well, so it's probably every few minutes. But in terms of kind of what the user sees, the kind of website and the kind of the immediate APIs that power it, we're making releases during the workday every 10 to 20 minutes, so fairly frequently. Some of those things you'll see directly, right? There'll be presentational things. Some of that will be under the hood things, or just maybe just to one part of the site. But there's a continuous process through. We have, as everyone does nowadays, a very automated CI process where as soon as things hit master and pass all the tests, they're immediately launched to live.
One of the interesting things about moving to the cloud is people tend to think of it as a technology move, but actually it's much broader than that. It's really a huge kind of cultural shift and a huge organizational transformation in a lot of cases. For something the size of the BBC, I'm imagining that could be very challenging.
There's so much we could talk about here. Teams have had to take on more. And of course, different teams react in different ways to that. One of the interesting challenges we've had, of course, is that the cloud gives you the opportunity to do so much and gives you so much technology at your fingertips in the way that when you had your own data centers, you really couldn't before. You had to have a much more controlled environment. And one of the challenges we had is to find the right way to control that, because every team going off and doing a different thing, that probably doesn't make sense from an organizational point of view. So how do you get that balance right between empowering teams and making them want to do that without diverging too much and having to find a way of bringing that in later? Ultimately, this is a transformation program, which large organizations, is always an interesting thing to do. It affects hundreds of people to change how they think, change what their day-to-day job is. That is a huge challenge. The amount of communication and ultimately persuasion you need to do is massive. And it was one of the things as we moved from the data center to the cloud. We didn't just want to rebuild like for like. We just want to lift and shift. We wanted to change our approach and what people were responsible for and how we built and how we made sure we weren't duplicating anything across teams and all those kind of things. And that's a huge challenge. You've just got to keep plugging away at it and getting people to understand where they need to be.
Right, yeah. I mean, any large-scale organizational transformation is always incredibly difficult. And then thinking about it from the individual engineer's perspective as well, you said that you'd moved to a kind of DevOps, you build it, you run it, you're responsible for your service running in production world. And again, if you're an engineer who signed up to work at the BBC before this transformation happened, that's a big shift in role and, out of hours and all the rest of it. Did you get pushback from that as well?
Yeah, we had that model where engineers had to be on call, right? You build it, you own it. I think that's really key to it. Yeah, it was for some people and not others. We were lucky, I think, that each team had enough people who were willing to be on call for it to be all right. And we have a very good kind of first and second line operations teams as well, keeping things going. So you only get called when there is a genuine issue. So it turned out to be all right in the end.
That's very interesting, actually. I guess if you've got first and second line support that's really strong, then that does reduce the risk of, fatigue and burnout and that sort of thing from your engineering team. That's actually a very good point. Matthew, thank you so much. I've really enjoyed speaking to you today. Really interesting conversation. And thank you very much indeed for joining us this week on the InfoQ podcast.